part of Chapter 4, as well as then the Project B kind of overview. So we'll have time to hit both of those on Thursday. So then that means then the following Tuesday, right, is an in-class work day for your Project B. So that just means I'll be available for questions. You'll have time to work on your project. And then Part B is then due the following Monday, right? So you want to make sure you're kind of on board, on target with those due dates. And so I had started out to just say that I'd had a chance to review the project, and for the most part, everybody's off to a good start. I feel like there were a couple of things from a professional standpoint that I would touch bases on. For whatever reason, the online students did a really good job of doing great cover pages on their project. I'm not sure, they maybe had some class but the majority of them have these like really attractive cover pages. Not a huge deal from a content standpoint, but just in terms of the professionalism of what they're presenting, it does look better. And then the other thing that I noted on most is that go ahead and put your diagrams on a separate page and then orient your diagrams horizontally. Do y'all know how to do that in Word? Okay, just because I think that what happens is your diagrams get crunched up because there's not enough room to stretch them out across the page, and it's hard to get the detail on them. And as we talk about Project B on Thursday, I'll hit a couple of other things that you might want to do that will kind of improve the quality of your diagram. And you have choices. You can draw the diagram in whatever tool you want. Word has all the parts and pieces. PowerPoint has all the parts and pieces, and you can copy and paste it in. Excel has all the parts and pieces. Whatever tool you're most comfortable with, that's what you want to use to go ahead and create your diagram, and just save it and then tweak it, and then you can copy and paste it in if you haven't actually created it in Word. And there's some of the tricks of the trade are you can attach those arrows to the shapes, right? So as you move the shapes around, the arrows move with the shape. So it's not like everything is in a kind of separate piece. And so that helps a lot, especially if you're having to make changes and you need to move things around. Then your arrows move as you move the shape, and you don't have to do that as an individual piece. So anyway, just a couple of suggestions there. But we're going to go ahead and move into Chapter 4, which is on flow time analysis. We were talking earlier you were talking about some classes that felt like kind of a kindergarten pace. And I feel like the content here, as we go through it today, it's like it becomes so obvious as we walk through it step by step. It might feel a little bit like that. But the reality of it is if we don't do that when you go to do your homework or when you go to hit on your project, it's not gonna tie together for you. So we're going to go ahead and walk through flow time analysis. And so flow time is the time of a given unit is the total amount of time required by that unit to flow through the process from entry to exit. So whatever your process is, you think about your process boundaries. Flow time is from when it starts into that process until it exits that process. Okay? And flow time includes both waiting time and activity time. Okay? And those are kind of important to understand because we're going to, deconstruct flow time into some different components. And the first two are going to be the activity time and the waiting time. So it's important because it affects the delivery response time. You think about Alex and his factory and how, when raw materials enter and initially how long it was taken for them to get the finished product to the customer. And especially if you start adding in that inventory that they have in that warehouse, right? Just the length of time that it takes to get inventory to the customer. And so the shorter the delivery response time, right, the more quickly you can collect your revenue. So if you think about, if you don't have all that inventory, you build it, you ship it, you collect your money, right? That's a whole lot quicker process and turn on your dollar than it is if you build it and store it. Right? And again, inventory is a tool. There are times and places where it's important to have it, but it isn't always of benefit to the process. So you have to, again, make a decision about how you're going to use that tool. Short flow times in the production and delivery process reduce inventory and the associated costs. Okay? So a shorter flow time in a firm's new product development process can be a competitive advantage. Think about being first to market, right? I'm sure you've heard about that in your marketing classes. And a shorter manufacturing process, you can delay production closer to sales. So, some things that we talk about in manufacturing, we talk about what's called the decoupling point, right? At what point can you, when do you have to tie exactly what you're doing to what the customer orders? And kind of the longer you can delay that in the manufacturing process, the more flexibility you have. So if you think about standardization in component parts, right? So if I have component parts that can be mixed and matched into different, and I can make those and then at the last minute put them together for my customer, right? Then I can delay that closer to the sale. Okay. Flow time is important because fast feedback and correction of quality problems. If you think about that inventory, let's think about Alex's warehouse where he's got all that inventory, and they find out that they've had a production problem. They have to go out and they have to repair all of that. So I think I did this conversation in 343. Have I talked about the cost of repairing on the production line in here versus, okay, because I was thinking that was 343. All right. So here's one of the things to think about when you talk about correcting quality problems, all right? So number one, if you've got a lot of inventory in the system, and we would have this happen sometimes at Pella, where we would be building product and putting it in storage to try to offset some of the peak production that we were going to see. So we might build in February or March, and it might still be in inventory in June or July, right? And then we'd find we had some type of quality issue. Well, that inventory could actually be buried by 1,000 units, right? And so now you have to move 1,000 units to get to the ones that you need to fix. And then, oh, by the way, you have to unpack them, repair them, and then throw away all that wasted packing material, right? And then repack them. So if you can fix a quality issue on the production line, so if you have good quality checks in place, what we would say in the window business is it might cost you $1. Right? If I can fix it right then and there, if I recognize it as I'm on the production line. If I have to go out in the warehouse and do it, it's probably going to be at least $10 a unit, okay? If it gets to the store and I have to go to the store and get the inventory and do things, it's going to be about $100 a unit, right? And if it actually gets to the customer and installed, right, we could be talking about thousands of dollars. So one of the examples that I use is there's a, and I'm sorry, I can't tell you the exact design of it, but there's a tube that goes into double hung windows that takes the water that might come down and it drains it out the wall, right? And so anyway, those were getting installed incorrectly, and so the water was being funneled into the wall. And so you can imagine as we caught those, because we had customer issues with double hung windows that were installed, it's not just the window now, you have to repair the wall and do all of that as well. And so again, you start talking about thousands of dollars because you didn't catch that quality issue on the production line. And some of that is just communication, right? No operator would intentionally create that kind of an issue, but it's because they didn't understand how important it was. I mean, to them it's this little plastic part, right? But it has to go in a particular way. And so again, you can talk about some design issues there. But flow time is also then considered an integrative measure of process performance. Okay, so how quickly a unit begins the process and ends the process tells us a lot about that process. So we have a couple of different ways that we can calculate flow time, right? We can use the direct approach. We can observe what's going on, right? Or we can use the indirect approach and we can calculate based off of information that we know. Okay, so if we're going to take the direct approach, you observe over a specified extended period of time. This is that staple yourself to the order approach, right? I'm just going to be that flow unit, and I'm going to time how long it takes. So then you select a random sample of flow units over a specified period, right? For each of those flow units, you measure the flow time from entry to exit of each flow unit in the sample, and then you take the average of it. So again, this is where I feel like it's a little bit, the direct approach is just observing, taking a random sample, and calculating based off of that. So when you're doing your project and you're calculating flow time, one of the things I want you to do is tell me, what approach did you use? Did you use the direct approach or the indirect approach? And if you use the direct approach, how many units did you sample over what period of time? And there isn't really a right in terms of if you have access to the information, then I want you to to use the direct approach and go that route. However, if for some reason that's complicated, it's not that I'm going to see that as necessarily bad, but I want you to just tell me what your assumptions are and how you got there, right? So I think that's an important piece. The indirect approach are the things that we've been working with Little's Law, right? Inventory is equal to throughput times flow time. So flow time is equal to inventory divided by throughput. So maybe you can observe average inventory, observe the process over a specified extended period of time. So this is kind of very similar, except for instead of observing flow time, we're just going to be taking snapshots of how much inventory is in the system at a given point in time. Select a random sample of points of time during that specified period, measure the actual inventory within the system boundaries, and compute the average of the inventory values measured. Okay? And so then almost always we know the throughput of a process and what we're looking at, right? So now we have both the inventory and the throughput, right? And so we can calculate the flow time. So on page 82, I'll go ahead and read that example. We'll go through that. So consider the process of credit approval at a small bank. To estimate the flow time of the process using the direct approach, so a sample of 50 applications was taken. For each application selected, flow time was observed. An average of the 50 observations was found to be 20.85 working days. So one of the things that you can do is you can, like if you said, well, we're going to study 50 applications, you can staple a timesheet to each application, and when it starts, somebody puts a time on it, and as it goes through each step, they put the time on it, and then it documents at the end. Okay, here's how long it took us to get through that. Okay. And so that's a direct estimate. To get an indirect estimate, right, a sample of 10 days was selected during a given period, and for each day selected, the number of applicants within the process was counted. So now we're counting, on average, how much inventory is in the system. Okay. The average of these 10 observations was found to be 215. Okay. Also, the throughput for the period was determined, and it was 10 applicants per day. So now, again, we can calculate it indirectly. Inventory divided by throughput, 215 applications divided by 10 applications per day is 21 and a half days. So pretty straightforward. 4.2 example. The research department of Golden Touch Securities is charged with releasing research reports for the benefit of Golden's customers and brokers. The firm's reports can be classified into two types: new releases, which require significant investment of research effort, and updates, which are much smaller in scope. In a typical month, the department releases 20 new releases for a combined value of $40,000 and 40 updates for a combined value of $20,000. On average, there are 10 open, unfinished new releases and 8 open updates. Okay, and so if we're interested in calculating the flow time, irrespective of type, right, we can add together that we have our throughput for the process is going to be 20 plus 40, which gives us 60 reports for the month, right? And our inventory we read was 10 and 8 for 18, right? And so based on those reports, so this is the 18 reports divided by 60 reports per month gives us a flow time of 0.3 of a month, okay? If we're going to do it based on dollars, right, we can get the average, the weighted average of the dollars in the system. So it's 24,000 divided by 60,000 gives us 0.4 of a month. So the reality of it is your unit may determine a little bit what your flow time is. Okay, so in this case, we have 0.3 of a month versus 0.4 of a month, and it's because we have different units. The other thing is, if you're estimating, you can be slightly off versus the direct approach versus the indirect approach. And the reality of it is, there is no perfect answer, right? We have too much random variation to ever think we're probably going to nail it exactly. And so what you're trying to do is you're trying to establish the information as best you can and make good assumptions and make those decisions on those assumptions. And that's what business is, because you never have it almost never do you have it exactly, right? You always are trying to figure out, okay, what's our best approach here? And so given that, right, it's important to document what your assumptions are. How did you get there? So a lot of times when I did cost accounting stuff or this type of work for different organizations, you list, and here's the assumptions, here's how we got this information. And then if someone in the room has an issue with that, now's the time to discuss it, right, before we make a decision and move forward, because you're asking these people to make a decision based off the information you're presenting. Okay? All right. So the process flow chart, we talked about a little bit. We hit it a little bit harder today. So in terms of what the graphical pieces mean. What I noticed is that those on campus actually did a better job with this than those online. And so I think probably you all caught it as we went through it, just kind of as an overview in chapter 3, and some of the online students maybe didn't spend as much time in that neck of the woods. Okay, and so again, your rectangles represent your activities. Okay, so activities is where something is being done. And what I have found in most cases is that for activities, it's typically easier to time them. Okay, the exception to that is if you're working with a process that has a long document flow time, right? And then it's almost easier either to take a snapshot of the inventory at each location and then indirectly calculate that flow time, right? But if you're talking about a manufacturing floor, right, it's easier to go out and somebody's doing something. It's easier for me to go time Julie and say, this is how long it takes on average Julie to do this, right? And so then I have the time and the throughput. Okay, the arrows just are the precedence relationships, how we link things together. Ovals are the events such as the beginning or end. And so really, I'm not super hung up on the fact that you need to have an oval at the beginning or the end, but that really is the only time you should have those on your diagram, is at the beginning or the end. Okay. Triangles represent the buffers or your waiting time. I was grading one project this morning, and I noticed that the student had buffer 1, and then buffer 1 was where there was a connection to a computer system, and then it waited, right? And I would suggest that that's probably that's a step and then waiting time. So inside your buffer, you shouldn't have activity going on, right? So that, because the way the process was described, there was some diagnostic that was going to be taking place. And so if you're going to hook it to so either you wait, you hook it to the computer, and you do the diagnosis. So those can be step beside each other, or you conclude it in one activity, right, with some sub-steps inside it, or it's hook it to the computer, wait, and run the diagnostic. But your buffers typically should not have activities inside them. When you find your path where you have to make a decision about what you're going to do, that's when you need the diamond, and that's when you have 2 arrows then coming out of the diamond that says, if the answer to the question is yes, you're going to go this way. If the answer to the question is no, you're going to go this way, right? And so that's what the diamond should represent on your diagram. Okay. And I think this is a great approach. I was grading one student on campus this morning, and I actually gave her some extra points back because the complexity of her project was such that she'd done a really good job of capturing the activities and putting them together in a precedence diagram. There were a couple of other pieces that she was missing. But one of the things I try to do is I try to compare overall quality and complexity across students, right? And so if you've got a complex project, but maybe you missed a step here or there, that's actually, you're probably still going to score better than somebody who's done something really simple and missed a step here or there, because I feel like we're not talking about apples to apples. And so just identify the activities that take place in your process, right? And so write them down, draft the activities into a precedence diagram, which you've kind of already done, okay? And you want to just check that to make sure that it makes sense, and then review to determine if there are any buffers or decision points that need to be added into your process. And they use a pretty simple project in example 4.3. And so I'm just going to read that real quick. So to illustrate the function of a simple process flow chart, consider the manufacturing process at Wondershed, a manufacturer of storage sheds. Okay. The process involves the procurement of sheets of steel that will be used to form both the roof and the base of each shed. The first step involves separating the material needed for the roof from that needed for the base. Then the roof and the base can be fabricated in parallel or simultaneously. Roof fabrications involve first punching, then forming the roof to shape. Base fabrication entails the punching and forming process plus a subassembly operation. Okay? Fabricated roofs and bases are then assembled into finished sheds that are subsequently inspected for quality assurance. A list of activities needed to fabricate a roof, fabricate a base, and assemble a shed is given in Table 4.1. Okay, so this is basically Table 4.1. That's that list of activities. Okay, and so then what we want to do is so here's that first step where we identify the activities, and then we want to put it into our diagram, right? And this is one of the tricks of the trade that I recommend is your diagrams can get really messy if you try to include everything on them, right? And so a lot of times I'll include a table below the diagram that has 1 through whatever and whatever. So anything that's on my diagram, anything that's on my diagram then has a number in it. And so if there were a buffer here, maybe that would be 2, right? But everything on there, and then I just list below what it actually is. So because this process, we're only depicting the activities, all the symbols are rectangles, right? That's all we're talking about here is the activities. And so often when you're diagramming a process, it's easier to number the steps separately from the actual diagram, and that makes the diagram easier to read. You'll note in your project, I request or require you to diagram the process in that way. However, your initial diagram will include the appropriate buffers as well. Okay, so as we talk about that, the flow time of a given activity is the time required by an average flow unit to flow through the activity. And note that the flow time of the process and of each of its activities consists of periods of activity interspersed with periods of waiting. So your activity steps can actually still have both activity and waiting inside them, right? But your buffers are kind of those pauses in between those steps that would not have any activity in them, okay? And so for the flow time of a process and each of its activities consists of periods of those activities and the waiting time. All right, so let's look at a simple example, right? So A, B, and C is a sequential process, right? Every unit that enters the process goes through every single step, right? So if each step takes 10 minutes, then the flow unit time is from the time it enters the process until it exits is going to be 30 minutes, right? Pretty easy to calculate, right? When we have what we call parallel processes, right? And so this is our example that we're talking about with the roof and the base, right? So we have path 1 and path 2, right? So the roof takes, I think, the upper path, and the base takes the lower path, and then the time is listed in minutes below it. Okay, so that being the case, if we're trying to identify the flow time, we don't sum up every single step in the process, right? We sum up the 2 paths and we find out which one is longer, right? And then the longer path is the flow time of the entire unit, because these 2 things are happening at the same time. So kind of the shortcut for me is I look at this and I go, well, that's 45 minutes on the top path, right? 35, 45, 75 on the bottom path, so it's going to be this path. The bottom path is going to be the longest path, and so the flow time is going to be the 20 plus the 35 plus 10 plus 30 plus 15 plus 40, okay? And so that's 150 seconds on that bottom path, and so that's the flow time for a unit through that process, okay? So the key thing that you need to make sure you're linking to in that problem is in a parallel process, you take the flow time across each path, right? And then the longest path is the flow time of a unit through that process, okay? And that longest time in project management terms is what we call the critical path, okay? And we talk about it as the critical path because if I wanted to increase the flow time for one of these Wondershed units, right? If I wanted to decrease the flow time, of one of these Wondershed units. If I decrease activity 3 by 5 minutes, is that going to decrease the flow time of the process? It's not, right? And so it's important to figure out what your critical path is, and as you're focusing your efforts to improve flow time, you have to focus on the critical path until such a point as you've improved it till it's no longer the critical path. And then that's why it's continuous improvement. Then you find the new critical path and you focus your improvement efforts on the new critical path. Okay? All right. So we've got this example where we're going to be analyzing process performance through a mortgage application. And we're going to show a couple of different concepts with this kind of simple example. So what's the minimal amount of time to process an input into an output in this? So first off, how would I get there based off of what we just described? Troy, how would I get there?
You have to determine which one's the longest.
Right. So I'm going to go 5, 25, and again, I can do the quick version and just compare the two parts that are different, right? The top path is 20 minutes and the bottom path is 30 minutes. So the bottom path is going to be my critical path. It's going to be 5 plus 15 plus 15 plus 15, which in my math is 15 minutes. Does that sound right? Okay. All right. Yeah. Okay. All right, so here's a different question. Okay, here's a different question. So one question says, how quickly, and this is important because it'll be an exam question, and I say that because I think I emphasize that every semester, and I always have students that don't get this one. So let's just, right now, I'm saying this is an exam question, right? So we identified the flow time for a unit through the process, right? But the other question that we want to ask is, what's the maximum number of flow units we can process per hour? Okay, so here's what's different about that. When we talk about the flow time of the process, we're talking about how long does it take from one unit to start the process to end the process. When we talk about how many units can we process per hour, we're looking for the bottleneck of the process. Okay? The bottleneck of the process is the slowest workstation that we have. Okay? And our bottleneck is the verified check employment, because we can do one unit every 20 minutes, right? And so if I said, well, how many units can I do in an hour? You're going to know how many units can we do in an hour? 3, right? And that's the maximum that can go through that process in an hour because of our bottleneck. Okay? So it doesn't necessarily, they're two different types of questions, right? And so we have to make sure that we're aware of, when we talk about flow time, how long does it take from when a process starts until when it exits the process? When we talk about maximum number of flow units, we're looking for the bottleneck to say what's the restricting factor in terms of volume that's going through there. Okay, so critical activities are about that input-output flow time response, right? And bottlenecks are about the throughput rate. So again, we've got kind of two different approaches there. Great. So theoretical flow time and the role of waiting. So flow time, we're going to kind of, like I said, deconstruct that today, is activity time plus waiting time. So theoretical flow time says the minimum amount of time required for a flow unit to flow through the process from entry to exit without any waiting or interruptions. So take all of your buffers out. Now you're talking about the theoretical flow time. And it's calculated by using data on activity time instead of flow time. So now we're breaking it down one step further, because we said that flow time is made up of activity time and waiting time, right? And then we've moved to theoretical flow time, which is only activity time. Inside activity time, we have value-added activity and non-value-added activity, okay? And I make a note that says it could be necessary but still non-value-added. So let me give you an example. Value-added activity, the simplest way to think of it is the action that you're performing actually transforming the product, and is your customer willing to pay for it? And if the answer to either one of those questions is no, it's not value adding. Okay? So, but it doesn't mean that a step may not be necessary. So for example, the young lady that did the Papa John's Pizza driver check-in process, that entire process is not value added because it is not transforming the pizza for the customer in any way, shape, or form. It doesn't mean that it's not necessary because there's DOT requirements that say that we have to have logs and we have to do that, right? But be aware that the more time you spend on those types of things, the less, effective you're going to be as an organization because they're not the things that matter to your customer, right? And so our goal kind of is, as we go through these projects, is first off, let's try to get rid of as much waiting time as we can, right? That's step number one. And then step number two is, of the activity that we have left, let's look at it and see what's value added and what's not value added, and try to get rid of as much not value added activity as we can. Okay? One of my examples from Pella, we have welders that weld vinyl together, right? And the welders are supposed to work and give a clean weld. And I don't know, probably 30% of the time, they leave a bump, right? And where it comes together and it melts too much and it gives a ridge. And so then the operator has to step in with a knife and cut that bump off in order to meet the quality specifications. That is completely not value added, right? And so if we could figure out how to make the welders work right so the operators didn't have to do that, we're going to reduce the time of that activity because 30% of the time they're going in and having to do something manual. Okay? But so as you're working through your process, you're going to get to a point where you're going to have to look at your activities and describe what's happening in there as value added or not value added. And your question should be, is it physically changing the product, right? And if it isn't physically changing the product, or if it is physically changing the product, is your customer willing to pay for it? And if the answer to either one of those is no, right? And so Julie and Miranda, as I'm thinking about your process, it's probably very much like that driver check-in process. The whole process is necessary. It has to be done. The reconciliation has to be done. But if in terms of adding value to a student at Murray State, you probably don't really want to have to pay extra because they're over there having to do a reconciliation, right? And so, again, so you're going to probably define your whole project as not value added, and what your goal will be is to get it down to as few of necessary steps as possible, right? So, and the thing is, it sounds judgmental, right? Because it's sort of a little deflating to hear, well, our whole process is not value added, right? So it's not meant to be judgmental, but it's meant to be a classification system and an awareness factor, right? So if you're an organization, where do you want to spend and invest, and where do you want to make sure you're getting the best bang for your buck? Okay. All right. So I've got a couple of examples that I'll go over here just to kind of be consistent. So in a beauty salon, the actual transformation, the haircut, is the value-added activity, right? When you go in and they give you a haircut, that's the value-added activity. Collection of the money is not actually value-added, right? It's necessary, right? But it doesn't transform what you're doing. And so the quicker they can make the payment process and that, the better off they're going to be, because that's not what you value, right? You don't, like when you go up to pay, I love this part of the process, right? No, nobody does that. So again, think about value added or non-value added. And so another kind of good thing to think about in terms of not value added, if at any point you have inspection as part of a step, right? It isn't that it's bad. It may need to be done, but it's not value added. Your customer wants you to do it right the first time, and they want you to have checks and balances in place so that you do it right the first time. They don't want you to have to go check it to make sure it's right. They don't want to pay for that, right? And so, again, that makes it not value added. All right, so again, we have those three components. We have, from flow time, we break it down into activity time and waiting time. And then from activity time, we break it down into value added and not value added. Okay? All right, so this process diagram includes activity times as opposed to the flow times. So now we're down to so what they were doing in that first step is they were including the waiting time in there. So So now we need to use the activity time to identify our theoretical flow time to see what's changed about this, okay? So again, we're down to activity times, and if I'm going to look, I'm going to say the top is going to be 15, 20, 30, 45, right? 45 minutes, and the bottom is going to be 20, 30, 40, 50, did I do that right? 20, 30, 40, 50, 65 minutes. So the bottom path is still our critical path, and so the theoretical flow time of the process is going to be on the bottom path, and it's going to be at 65 minutes. I wonder if I added wrong somewhere. We'll see. 5 plus 15 is 20, plus 5 is 25. 35, 45, 50. Yeah, I added wrong. Sorry, it's 60 minutes on the bottom process. So therefore, theoretical flow time is 60 minutes. So our average flow time, right, we determined from that first part of the process was 150 minutes, and our theoretical flow time is 60 minutes. So when I go to calculate my flow time efficiency, it's the theoretical flow time divided by the average flow time. So it's 40% is what our flow time efficiency is. So those are sometimes aha moments, like when we get to flow time efficiency and you go, okay, so what we're saying is 60% of the time we're not doing anything with the product. It's just waiting, right? And so if you think about being able to, move from the 150 minutes to the 60 minutes, how much faster that product's going to move through the process, right? Back in the early 90s, if we looked at the whole process from the time that the customer placed the order until they received the order, it wasn't unheard of for that to be the flow time efficiency to actually be somewhere around 3 or 4%, right? And so those were huge opportunities. Interestingly enough, they started out looking at those flow time opportunities just inside the factory walls, right? And they put the screws to everything that was going on in manufacturing. You have to be better. You have to be better. You have to figure out how to get our flow times down. Okay, then as we got smarter, we said, well, let's look at the bigger picture of the process. And a lot of the administrative stuff is what was taking days to get done, right, on both ends of it. And so then it's like, okay, well, let's not just focus on what's going on inside the factory walls. Let's look at the entire process, and let's figure out how we can reduce those flow times. So when just a couple of years before I started at Pella, their custom window was, you call me and tell me what you want, and I'll give you a date, and it's probably going to be 2 months out is when we're going to get you the custom window that you want. And then I think they went to 20 days, and then when I got there, they were at 15 days, and before I left, we were down to 11 days, right? And we were 99.9% on-time delivery, full order. So, and that was just about focusing on the process and how can we reduce that time, and that was a lot of the administrative time as well as what we were doing inside the factory. Okay, so when we adopt a process view, we have some questions that we should be asking. And you've asked some of them already. So what's the process boundaries? What's the input and output? What's the flow unit? So you can attach yourself to that flow unit and record your process steps. Okay. And so as you're doing that, you're asking yourself, what are the value added and necessary activities? And what are the associated processing times or work content? Okay. Where does the flow unit wait? So what are those buffers and what are those associated waiting time? What are the routes a flow unit can take? What are necessary precedence relationships? What must be done sequentially? And note that the first improvement step will be to delete the non-value added and unnecessary activities and buffers and waste. So that's why you're spending that time to try to identify it. How can we get rid of it then? If it doesn't matter, how do we get rid of it? Okay. So then another question to ask is, who does the work? Okay, and we really start to focus on resources in Chapter 5, but you need to be thinking about that as you're putting together your Project B, that part of the project. And so what are the activities that a given resource performs? Okay, does cross-training or flexibility, would that help that? What are the resource constraints? Okay, what determines the flow rate, the demand, or the capacity? Okay, how is quality measured? And what is the cost of each resource, right? So those are going to be kind of all things that you want to be considering when you're thinking about your process. What information is required to perform each activity? So again, we have a lot of times we have a physical flow and we have an informational flow, okay? So you need to make sure that you know how that comes together, okay? And at the end of each of the next, I can't remember, it's 2 or 3 chapters, we're going to have these levers to manage. In this case, we're focused on flow time, so the levers are going to be to manage flow time. And so when you get to that part of the project, which I think is going to be part C of your project, right, I ask you to address the levers for reducing flow time. What I want you to do is come back and hit every one of these levers and say it applies to our project in this way, or it doesn't apply because of this. Not everything is going to apply, but some of them will, okay? And I want you to consciously think through each one and see how it applies to your project or doesn't, okay? So if you want to reduce flow time, right, if we can take work content from critical to non-critical activities or to the outer loop, meaning, so if you think about on the that path that we diagrammed where we had the upper path and the lower path, and now we would say, okay, well, but we can take 5 minutes of work from the critical path and move it to the non-critical path, right? You've now increased your flow time by 5 minutes, okay? You can reduce non-value adding activities by working smarter, right? So rather than, trying to think of some of the examples that we've come up with over. A lot of times the working smarter for me comes from you'll have somebody that's worked on the production line for 15 years and you'll have somebody that's brand new and they're not doing it the same way, right? And that working smarter comes from the guy that's been doing it for 15 years or the gal that's been doing it for 15 years going, here's the best way to do that and here's why, right? And so a lot of times it's just an experience thing, but if you can document that, then you're going to save everybody some time, okay? Reduce the amount of rework, right? That's a quality issue. Modify the product mix, okay? So this one, I think, the example that I like to use here is when I worked at Pella in Story City, we had what we called the MP line, and it was the multi-purpose line. And so the multi-purpose line had the ability to do, it had 2 sash areas and then went into 1 frame area, okay? And so 1 sash area was venting units and 1 sash area was fixed units. And so as we brought those 2 together, right, and then sometimes we would have customers that would order twins, triples, or doubles, right? And so we would take those units, we would pack them in brown cardboard and put them up in the rack, and then there was a line that would then put the twins, triples, and composites together. Quads is really what they were, twins, triples, and quads. So they'd have to go pull those units back out, bring them back to the composite area, composite them, repackage them with the pretty packaging as opposed to the plain brown packaging, put the labels on them, and ship them out. Okay. Well, when we talked about modifying the product mix, we had the ability we knew how long it took to do a venting unit, we knew how long it would take to do a fixed unit. And so what we knew is that we could do basically 2 venting units for every fixed unit that we were doing. And so we set up the schedule to actually create 2 vents and a single, 2 vents and a single. 2 vents and a fix, 2 vents and a fix, right? And then we knew how long it would take for them to put it together, a twin, triple, or a quad. And so we would break it out on the schedule. It was a complex piece to put together, but once we got it figured out, then it would send single, single, twin, right? And the twin would go, and we added a piece to the line, and it would send the 2 singles and to that composite area. So we eliminated all of that packaging, all of the shrink wrap, all of the labor involved in terms of coming off of that production line, putting it up, going and getting it, bringing it back, and all of the trash, right? And I can't remember exactly the savings, but I'm thinking it was somewhere in the neighborhood of $100,000, right? And so you're going, okay, that's pretty cool. But the reality of it is we modified the product mix, and we actually slowed that production line down. But it was a bigger win in the long run because we eliminated all of those other steps in the process, right? And that's doing exactly what we're talking about here, looking at that entire process and going, what's waste in this process and how can we eliminate it? And then making the adult decision to say, because in a manufacturing environment, everybody wants to do more, quicker, faster, right? And to go, right, but more, quicker, faster isn't always better, right? If we can eliminate all of this, slowing it down is actually a better approach, okay? Of course, then the next one is increase the speed of operations, right? Which is, again, in the manufacturing environment, that tends to be the focus of, well, how can we do that? How can we do that faster? Okay? All right, so I thought we'll end class today with a few examples, and there are going to be ones from the exercises at the end of chapter 4, and so I'll walk you through a couple of those. So this first one, they give us a table at the top of page 96. And the traffic court of King James County, I think that's an interesting county name, operates between the hours of 9 a.m. and 1 p.m. Each morning, roughly at 9 p.m., 200 defendants show up for trial involving traffic violations, such as speeding, illegal parking, and ignoring a stop sign. On Monday, June 10th, a sample of 10 defendants was selected at random by a consultant, and for each defendant, the consultant recorded the actual time spent in discussion with the judge and the time paying the fine, not including waiting. Also recorded were the times the defendant arrived and left the court. The data are summarized in the table 4.7. Okay, so again, 9 a.m. to 1 p.m., 200 defendants show up in court. They take a sample on June 10th, 10 defendants selected, and 10 defendants selected at random, and then here's what that table looks like. Okay, so we've got the arrival time, the departure time, the time with the judge, and the time paying fine. Okay, so if we were going to identify, if we were interested in activity time, what are the actual activities? So activities, again, that's a non-judgmental, we're just interested in when are they actually doing something. What are the two categories that we have for that?
Time with judge and time paying fine.
Time with judge and time paying fine. Pretty much everything else is waiting time, right? So we look at that, and the first step is to find the average flow time for waiting time with the judge and for paying the fine. And so we can do that by estimating the average of the total time each defendant spends in the system. Okay? So the average of the total time that people spend in the system, if we sum this up, you can do that. Just trust me, I did. It's 120 minutes. Okay? And if you want to play with it, if you're a nerd like me, if you want to play with it, you can actually set it up. Excel will calculate. You can do addition and subtraction based on time, which I think is a pretty cool thing to, and it doesn't take that long to figure it out, but it's kind of a fun thing to do. Okay? Okay, again, there's my geek exposing itself, all right? And so then the theoretical flow time of the process, which is activity time only, right, can be estimated by averaging the activities and not the waiting, okay? And so it's a minute, 1.55 minutes and 2.4 minutes respectively for time with the judge and the time paying the fine. And so thus the theoretical flow time is 1.55 plus the 2.4, which is 3.95 minutes. So I just averaged this column and this column, right, and added those together, and that's our activity time, or our average activity time, theoretical flow time. And then when we calculate flow time efficiency, we're dividing the theoretical flow time by the actual flow time. So 3.95 divided by 120 minutes is 3.3%, right? So that means that of the 120 minutes, 97% of it is not value. I mean, they're just waiting, right? And so, again, if you were concerned about the customer, and again, this is about a power relationship, right? Who's got the power in that situation, right? So, but it's interesting to look at things from that perspective.
Can you
Okay.
say, what was B again? Can you say those numbers again?
1.55 minutes for the average time with the judge, and 2.4 minutes for average time paying the fine. And when we add those together, it's 3.95 minutes. Okay?
Thanks.
All right, so then 4.2 says, Wondershed, our example that we had in class earlier, produces, in addition to the standard model, a deluxe version for the discriminating customer. You gotta love that, the discriminating customer, right? The production process for the two models is identical and is depicted in Figure 4.1. The activity times for deluxe models is listed in Table 4.8. Okay, so all I've done is take that and combine it onto the chart, right? So again, we have the roof going across the top and the base going across the bottom. All right, so we want to compute the process flow time for producing a deluxe shed. So, Austin, I'm going to pick on you.
Okay.
If I want to determine the flow time for a deluxe shed, what am I doing? What's my rationale here?
Say that again.
So I want to determine the flow time. What's the process I use to figure the flow time out?
The total.
Mm-hmm.
Add up both processes.
Mm-hmm. Add up both paths.
Yeah.
And then which do I select, the longer or the shorter?
The longer.
The longer, right? Okay, and so again, I usually take that shortcut so that the top part that's different from the bottom part is 90 minutes across the top, and it's 35, 45, 75 minutes across the bottom. So that tells me that my longest flow time is going to be the top path. And so when I add it together, we're going to see if my math is any better now. 20 plus 45 is 110, plus 25 is 135, plus 40 is 175. Does that sound right? Must. Okay, so that's going to be our flow time there. And so, all right, then Blake, what's the impact on the flow time of the process if the flow time of activity 2, which is here, right, is increased to 40 minutes?
Of activity 2.
So if I increase this by 5 minutes, what's the impact on the flow time? What's that?
I mean, it's going to be longer. I'm not sure exactly what you're asking. Sorry.
Okay, so then the question is it really going to be longer? It's not? Troy, why isn't it going to be longer?
Because it's still
Shorter,
less than,
yeah.
it's still,
Oh, okay.
so that's the key there, right?
Okay.
So again, we're getting to that point of, if we're trying to decrease flow time, you have to find the one that is the critical path, and that's where you play with it at. And in the opposite of that, if it's not the critical path and you add time to it, as long as it's not making it longer than the critical path, you've not changed the flow time of the process, right? So it's kind of that perspective. So it was a little bit of a trick question. So, and what's the impact on flow time of the process if the flow time of activity 3 is reduced to 40 minutes? So what would be the impact, the net impact?
It'd be 5 minutes shorter.
There you go. Yep. So again, do you see why I'm a little bit like, this is a little bit like that, the basic class, but it's almost like if you don't make those connections, then you're not gonna track those through on your project. Okay. All right. And then let's reiterate, because it's going to be an exam question. What would be the bottleneck of this process?
The 3 or
5, right? Both of them are, but that's the bottleneck, right? And so that's going to limit how many units you can do, because it takes 45 minutes, so you can say I can do 1 unit every 45 minutes. And so, that's the actual, confines the rate that you can do things at, okay? And then the path is the flow time of the process, okay? All right. So, this one is always interesting because when students have done this in the past without me doing the project first, or doing the diagram first, right? They describe more steps than this, okay? But they define the boundaries, and so it's kind of a boundary type question to begin with, right? You have to get the boundaries right of what you're drawing first, and then you can get the rest of it right, okay? And so the Evanstonian is an upscale independent hotel that caters to both businesses and leisure travelers. Okay, when a guest calls room service at the Evanstonian, the room service manager takes down the order. Okay, so taking the order is 4 minutes, right? The service manager then submits an order to the kitchen, okay, to begin preparing the food. Okay, she also gives an order to the sommelier, I don't know if I say that right, but that's how I say it, to fetch wine from the cellar and prepare any other alcoholic beverages. Finally, she assigns the order to a waiter. So it takes 4 minutes to take down the order and to assign the work to the kitchen. So that's here. I pointed the screen like you can see that. Okay. And then it's assigned to the kitchen, right, to the sommelier, and to the preparing the cart. Okay. It takes the kitchen 18 minutes to prepare the typical order. It takes the sommelier 6 minutes to prepare the drinks for the order. While the kitchen and the sommelier are doing their task, the waiter readies the cart, puts a tablecloth on it, and gathers silverware. This step takes 10 minutes per order. Okay. Once the food, wine, and cart are ready, the waiter delivers it to the guest room. It takes the waiter 12 minutes to deliver the meal to the customer. It takes the waiter an additional 4 minutes to return to the station and debit the guest's account. All the times mentioned represent flow time at the various activities and include the effects of waiting. Okay, so draw a process map for the room service process from receipt of order to delivery of the food, right? That's oftentimes that first mistake that students will make because we add 2 extra steps, right, that were described that were about returning the cart and actually accepting the payment. So it's kind of okay, we got to make sure that we're identifying the boundaries and following through. And then it says, what's the flow time of the process? So Khalid, what's the flow time of this process? How would you figure that?
You add the activity and the waiting time.
Okay, so and in this case, we have the waiting time is included in those steps. So what is the flow time of this process?
4 plus 10 and 12, 6. Right.
So say that to me again.
You add 4 minutes and 10 minutes and 12 and 6.
Okay, everybody agree with that? I think in the end you'd get there, but it's not the way I would have gotten there. Because you didn't add the 18 minutes in, did you?
Oh, no.
Okay, but you're 12 and, well, no, not quite. So no, that's not right. So what you're doing is, on these things that are parallel, you're looking for the longest path. And you're only going across the longest path. Or you can add up every path and say, okay, this is the longest, right? But so in this case, it's going to be 4 plus 18 plus 12, okay? And so I'm saying that that should be 22 plus 34 minutes. Okay? All right, so that's going to be our flow time. That's how we get our flow time. And what's the effect on the process flow time if the waiter could prepare the cart in 8 minutes? Chelsea, what does that do? So the waiter can reduce his time by 2 minutes.
Doesn't change it.
Good answer. It does not change it because it's not on the critical path. Okay? All right, and then let's come back up to Troy. What's the effect on the process flow time if the waiter could deliver the order in 10 minutes instead of 12?
Or reduce it by 2.
It's going to reduce it by 2. Okay, so then it says now redefine the process. And to begin upon receipt of the order and end upon debit of the account and repeat the parts A and B. So all we would do here is just add that return and debit for 4 minutes and we refigure everything. And it still would be, the critical path would be across the top because that's the longest of those parallel paths. Right? We would just add 4 minutes to that. Okay. All right. That is the end of the examples that I have for you. So again, they're not hard, but it's just kind of making sure that you understand the difference between the flow time, right? The theoretical flow time, and the value adding and non-value adding, right? And then I also think the other key thing is understanding when we're talking about critical path and the flow time of a process versus the rate that something can go through where we're identifying what the bottleneck is and saying that's the fastest it can calculate. It can only do 1 unit in this case so our bottleneck here would be preparing the food at 18 minutes, right? Okay, that's what I got for you today. I'll see you back here on Thursday. We'll finish up with the appendices from Chapter 4, and we'll take a look at the project for Part B, okay?